7.3, geometric distributions. In the last lesson, we learned about binomial distributions. So binomial distributions, the key is that there was success and there was failure. So we could have had one of two options. Today, many of the questions really could be phrased almost the same way, except for we're going to look for one different thing, is that it's going to be about waiting time. And so that's our key word in here, is the waiting time or the waiting period, which really is just referring to the number of trials before a specific outcome occurs. And what happens in this geometric distribution is that we stop once we get the thing we want. Okay, so in the textbook it walks through on page 388 an example of the game of Monopoly, where if you roll doubles, then you actually get out of jail. And this is a type of geometric distribution, except for in Monopoly, the real game, you actually get out after 3 rolls and you just have to pay money. But imagine if they modified the rules, and you would just keep playing until you got the doubles. And keep rolling every time. When you got doubles, finally you can get out of jail. So calculate the probability distribution for getting out of jail in X rolls of the dice. So what we can imagine here is we have X rolls of the dice, and we have the probability of having that. We say, well, there's the possibility that and I'm going to phrase this in a different way. We're going to say in 0 rolls, as in 0 means no waiting, as in you get it on your first try. So we'll think about it that way. So probability you get it in 1 roll. Well, doubles, we got to think about the probability of getting doubles. So there are 6 ways to get a double. That's 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, and 6 and 6. Out of the, which we know is with 2 dice, you have 36 options. So there's a 6 in 36 chance, or 1 in 6 chance you get it in the first roll, so there's absolutely no waiting. Now next, and 1 in 6, by the way, would be approximately 16.7%. There's a possibility you could wait 1 time. So if you wait 1 time, that means you failed once, which is a 5 in 6 chance of not getting a double. And then you would get what you want, 1 in 6. So 5 in 6 over 1 over 6 is 5 over 36. And 5 divided by 36 is 13.9%. We could do it in 2 rolls, meaning you fail 2 times. So that means you don't get doubles, and then you don't get it again. So it's 5 over 6 times 5 over 6. So we could just say squared times 1 over 6. And now we have 25 over, just going to make sure my numbers here, over 216, and 25 divided by 216 is 11.6%. So you'll notice that this number is just slowly going down bit by bit. And if we were to want to know what would happen with 3 rolls, that would mean you wait 3 rolls. So that's 5 over 6 to the power of 3 times 1 over 6. And we would just continue this process. So notice that what's happening here is that this power is just increasing by 1 each time, because we have 1 more fail before we get the thing that we want. The other thing I want you to notice is that this now is always just to the power of 1, whereas with a binomial distribution, that was changing because we could have multiple successes. But in this geometric sequence distribution, we're only going to succeed. And once we succeed, we're done. We quit. We're done. So we don't have to worry about different orders. We don't need to worry about how many times we succeed. We simply just succeed and then we quit. Now, how many times would you expect to roll a die before you actually get what you want? That's B. So estimate the expected rolls. Well, I'll give you the formula and you'll see it below. The expected value formula is Q over P, where Q is failures and P is success. So the probability that I fail is 5 over 6 at getting doubles. Probability that I succeed is 1 over 6. If you divide those two, you're going to get 5. And what this formula tells you is that you expect to fail 5 times before you succeed. So another way to say that same sentence would be, you would expect to succeed on the 6th try. All right, just take a look at these formulas here. P of x equals q to the power of x times p was what we were using up here to have happen. But we kind of figured that out organically, but that's the formula you're using. We have our expected value, and we're going to try out these 3 questions from the textbook real quick. But first, I just want to remind us what's different between a geometric distribution and a binomial. Geometric, there is one success at the end. Binomial, you could have multiple successes in any order. Okay, so that's the main difference here between those two. And then, of course, their formulas are quite different. Okay, 3 questions from the textbook. We're going to look for that waiting time word, okay? So which of the following situations is modeled by a geometric distribution, and explain your choice. So rolling a die until a 6 appears. Well, notice they're waiting until. So this is geometric because they're going to quit as soon as they get what they want. B, counting the number of hearts when 13 cards are dealt from a deck. So you could have multiple hearts. You could have 1 of them, 2 of them, 3 of them, more of them. So this is binomial. We're kind of seeing this as success is getting a heart, I guess. Predicting the waiting time when standing in line at a bank. Predicting the waiting time, so you're waiting how long until. This is geometric. How long until I get seen? D, calculating the probability of a prize being won within the first 3 tries. Within indicates that it's not the last thing that happens. So it could happen at any point. So this is binomial. Lastly, E, predicting the number of successful launches of satellites this year. Well, I hope we have multiple successful launches. So I would say that's binomial. There could be multiple. 3, for a 12-sided die. 12-sided die means there's 12 sides, by the way. What is the probability that the first 10 will be on the 3rd roll? So that would mean on the first attempt, you don't. On the second attempt, you don't get a 10. And on the 3rd attempt, you get a 10. So how would that be figured out? So we're going to assume that each side of the die has a different number on it. So if you're going to fail at first, there's an 11 in 12 chance you don't get a 10. And then, so we multiply, there's an 11 in 12 chance you don't get it again. And the probability you get it on the 3rd try would be 1 over 12. And so we just multiply that out. And you get 7%. B, what is the expected waiting time until a 1 is rolled? Well, again, that formula, E of x equals Q over P. So Q is failure, so that's 11 divided by 12 over success, which is 1 over 12. If you divide those two things, you get 11. So you expect 11 fails before succeeding. Question number 5. To finish a board game, Sarah needed to land on the last square by rolling a sum of 2 with 2 dice. She was dismayed that it took her 8 tries. Should she have been surprised? We can look at the expected value here because we want to know, well, what should Sarah expect? She seems to be disappointed by what happened here. So expected, how many ways are there to get a 2? So the probability of getting a 2, by the way, there's only one way to get it, and that's getting a 1 and a 1. So there's a 1 in 36 chance of getting it. The probability of not getting a 2 would be 35 over 36. So expected would be 35 divided by 36 divided by 1 over 36. And if you divide those two, you get 35. Okay, let's try and check in with Sarah again. She says she was dismayed that it took her 8 tries. Well, I would say, actually, you did really well there, Sarah. You expected 35 tries before succeeding. But it only took 8. So if I were to put a whole bunch of people in a room, I would say she was actually pretty lucky compared to the average person in that room for how quickly she got her sum of 2. All right, so that's binomial distributions. Sorry, geometric distributions. You're going to work through this question here. Remember that a probability distribution means showing all possible answers. But this is the expected waiting time. Yeah, you can't show the whole chart because it's possible you could go to Tim Hortons 100 times, buy 100 cups, and fail every time. But at some point, the probability gets closer and closer to 0. So there's that one question, and then there's 3 questions right here in your work. And so you're going to try that out.